Welcome back to the Explainer. Have you ever actually wanted to peel back the digital curtain and just look directly inside an AI's brain while it's translating languages? We hear about these massive black box AI models all the time, right? But today, we're doing something totally different. We are looking at a really cool project called the mini-translator. It's a neural machine translation model, or NMT, built completely from scratch. And by looking at this beautifully contained little project, we get this incredibly tangible, visual way to understand the exact mechanics of how artificial intelligence processes, maps, and translates human language. Today, we're going to see exactly how that neural machine operates.
Here's our roadmap for deconstructing this model piece by piece. First up, the real language challenge. Then, building the architecture. Next, visualizing AI thought. Fourth, measuring success. And finally, taking it from a basic CPU to production. Don't worry, we're going to make the complex mechanics super accessible.
Okay, let's dive into this. To really appreciate what our mini-translator is pulling off, you kind of have to understand its lineage. The project we're exploring today is actually step 7 in a comprehensive series of mini-language models. So it builds upon this massive foundation. It started with word2vec, just to understand word vectors, then moved through self-attention, basic transformers, GPT architecture, chat instruction formats, and finally cross-attention. Our English to Spanish translator is the magnificent step 7, bringing all of those preceding highly technical concepts together to solve a real-world problem.
Section 1. The Real Language Challenge, taking us from English to Spanish.
We are making a massive leap here. We're going from processing simple synthetic data to tackling actual messy human language. Notice the stark contrast between where the AI was back in step 6 and where it is right now in step 7. Previously, the AI was literally just reversing digits. That's a purely synthetic programmatic task, right? It used a shared vocabulary of just numbers, and success was measured by a simple token accuracy. Basically, did it get the number right or wrong? But human language isn't that simple. Step 7 takes on real English to Spanish translation, meaning we're suddenly dealing with two completely separate vocabularies, an English encoder and a Spanish decoder. We've totally abandoned that simple accuracy metric for something a lot more nuanced. Basically, the AI is stepping out of a sterile lab environment and right into the complex reality of how humans actually speak.
Section 2. Building the translation architecture. Let's build the brain.
And this brilliantly illustrates the how. How do we physically construct a digital brain capable of handling all that linguistic messiness? Well, if we look at the configuration parameters of our mini-translator, we can see exactly what we need to give our model the sheer capacity to handle real language. Notice the scale-up from the previous steps here. We're rocking an embedding dimension of 128 because, well, a real vocabulary demands serious capacity. We're using 4 attention heads, and crucially, we're deploying 4 encoder blocks and 4 decoder blocks, along with a feed-forward dimension of 256. We're adding real depth and complexity so the AI can actually capture the intricate relationships between English and Spanish words.
But you guys, here is the number that is truly staggering: 140. Despite the robust, multi-layered architecture we literally just looked at, this model trains on just 140 highly curated sentence pairs. It doesn't need some massive millions-of-dollar supercomputer. You can train this entire thing on a standard laptop CPU in just 5 to 10 minutes. Honestly, it's a massive testament to how efficient neural networks can be when the architecture is just designed perfectly.
Section 3. Visualizing AI thought through soft alignment.
This is where things get really fascinating. I want you to actively think about this question. How does the AI actually map English to Spanish? Remember, we didn't give it a hard-coded English to Spanish dictionary. We didn't program any grammar rules, nothing like that. We just gave it sentences in English, the corresponding sentences in Spanish, and basically said, hey, figure out the math in between. So how does it bridge that gap?
The answer is this super cool phenomenon called soft diagonal alignment. Through a mechanism called cross-attention, the AI learns to map the languages visually. When you plot the AI's attention weights, you get this really bright visual pattern moving straight from the top left down to the bottom right. This diagonal proves that the model is actively learning that English and Spanish generally share a similar word order. It shows semantically corresponding words aligning across the two totally different languages. You are literally peering into the AI's mind and seeing it connect the concepts.
Now notice how the visual pattern here isn't a perfect razor-sharp line. The weights aren't just a strict 1.0 on a single corresponding word. It's kind of fuzzy, right? Why is that? Well, it's because the AI is actually smart enough to realize that direct one-to-one word swapping just doesn't work in the real world. Spanish grammar requires checking the surrounding context. It has to look at articles. It has to understand that verb conjugations depend entirely on the subject. So the AI dynamically spreads its attention out slightly, looking at the context around the target word to make sure it gets the grammar exactly right. That fuzziness? That's actually visual proof of advanced linguistic comprehension.
Section 4. Measuring success using the BLEU score.
Okay, so the AI is thinking, and it's aligning concepts, but how do we actually grade its homework? Because human language is so incredibly flexible, simple token accuracy, like checking if word 3 exactly matches word 3, is practically useless now. Instead, we use what's called the BLEU score. BLEU essentially measures the overlap between the machine-generated translation and a pristine human reference text. It looks at phrases and short word sequences, or n-grams, to see if the semantic meaning and flow match up, even if the exact word order varies slightly. It is absolutely the gold standard for evaluating real translation success. Let's look at how this builds our proof.
To prove the AI actually learned, we can look at the tangible outputs it generates, specifically its layer-by-layer sharpening. Across the 4 attention layers we built, notice how the soft diagonal alignment visual gets sharper and way more defined as the data moves deeper into the network. From layer 1 to layer 4, the AI becomes progressively more certain of the translation with every single layer it processes. It's so cool to see.
Section 5. From CPU to production. Let's look at the big picture.
So how does this tiny project fit into the massive macro world of tech giants? Well, so the crucial point is this. We just dissected a tiny model that trained in 10 minutes on a standard laptop CPU. But the fundamental cross-attention principles, the separate vocabularies, the soft diagonal alignments, and the BLEU score evaluations used in this mini-translator, they are the exact same core mechanics powering massive production systems like Google Translate. By understanding this micro-model today, you have just grasped the architectural foundation of global enterprise-grade neural machine translation.
I want to leave you with this one provocative thought. We just watched a neural network figure out the complex nuances of Spanish grammar. Articles, context, subject-dependent conjugations, the whole shebang, using merely 140 curated sentences, trained in just 10 minutes. If an architecture is this hyper-efficient at learning human concepts on such a microscopic scale, what could it achieve when trained on the entire internet? The mechanics are exactly the same, only the scale changes. Thank you so much for joining me on this explainer. Keep learning, and I'll catch you on the next one.